analogous to a matrix eigenvalue problem, which is A minus lambda I into x equal to 0. So, we have defined a regular Sturm-Liouville system for a differential equation. Okay. So, you are given a differential equation, so you have an operator L. Okay. You can put it in some nice form, a derivative so with some reduction. So, we have defined kind of normal form. So, that is L, Ly equal to lambda y, y is the solution. So, for this equation on a finite domain in the interval a b, you have defined you have given some boundary conditions. So, for which you provide these boundary conditions when the p of x, the coefficient of second order term, second order derivative, if it is non-zero at the endpoints, then it is called regular Sturm-Liouville system, for which you have given the boundary conditions. This eigenvalue problem Ly equal to lambda y with these boundary conditions, it is a regular Sturm-Liouville system. So, so why we define these boundary conditions? In order to make L is Hermitian, okay, in order to make the operator L, differential operator L to be Hermitian or self-adjoint or skew symmetric. We can also do in a different way when P of A equal to 0 or P of B equal to 0 or P of A or P of both of them are 0. When also in other case you can also do make it the operator you can make it Hermitian when P of A equal to P of B. Okay. So, these two cases we will see later. So, before I see them we will try to give the regular Sturm-Liouville system some examples. Okay. We will just do some examples for the regular Sturm-Liouville system. So, this is the regular Sturm-Liouville system we have seen. So, this is together. So, if you are given an equation like this, you have these boundary conditions like this. So, you can find the eigenvalues and eigenfunctions like I explained in the steps to do, find the eigenvalues and eigenvectors. And once you see this, if you see all the eigenvalues are distinct, then corresponding eigenfunctions are orthogonal with respect to the dot product that is defined based on your operator L. And once you have this, once you get all these eigenfunctions, they form orthogonal, which you know, and they are complete. That means any function f I can write in terms of this, any actually square integrable function you can write in terms of these eigenfunctions. Okay. So, that is actually a Fourier series, and then how do these are arbitrary constants, Cn's are arbitrary constants, those things you can find just by using the dot product. So, make a dot product both sides with Vn's so that you can get your Cn. Okay. So, we will see some examples how we do this. So, what we do is we make a problem like problem find eigenvalues and eigenfunctions for the regular SL system. That is y double dash of plus y double dash plus lambda y equal to 0. Lambda is a parameter and your domain is between 0 to 1. And the boundary conditions are given as y0 is 0, y at 1 equal to 0. So, these are your boundary conditions. So, this is your system. So, how do I solve this? I need to find eigenvalues and eigenfunctions. So, first we want to see, put it as the equation where lambda is a parameter, this you put it as the eigenvalue problem. What is the eigenvalue problem? So, you know, so for a matrix A x equal to lambda I, the lambda x, okay, lambda x, this is your eigenvalue problem. So, try to look for x for which for each lambda values, okay, fix your lambda or find those values of lambda for which you have a non-zero solution x. Those are your eigenvalues and eigenvectors. So, you do the same thing. So, try to put this equation in this form first, that I can write like earlier. So, this is like my is 0, okay, my is like my equal to 0, m is the operator. So, m is actually same as L, you can see that, okay. So, this second order differential equation I will put it in a nice form. So, the form which looks like a self-adjoint. So, that is y dash of dash. So, this is like d dx of dy by dx. So, this is 1, p of x is 1. So, that is what we are putting. So, plus q is 0, okay, 0 into y plus lambda into 1 into y equal to 0. Okay. So, from this you can recognize what is your p of x. P of x is 1, q of x is 0 and w of x is 1. The moment you see w x equal to 1, immediately you can define the dot product is dot product of any functions is simple 0 to 1, that is your domain, f x g x into w x, which is 1, okay. So, dx. So, this is your dot product. Then it is actually easy to find the and you see that this is you know that with these boundary conditions you have seen that this regular Sturm-Liouville system is self-adjoint. So, we know that since it is regular Sturm-Liouville system, since L is self-adjoint or Hermitian, we have seen yesterday, okay, these kind of things are actually Hermitian. Since this is this, lambda is always real. There is a property of self-adjoint or symmetric or skew symmetric matrices, values of the eigenvalues are real. So, that is what we are analogically we are seeing this here, even here it is true, but we are not proving it, okay. So, you have this lambda is always real. So, if lambda is real, we can think of 3 cases: lambda is positive, lambda equal to 0 or lambda is negative. So, these are the 3 cases you have possibilities, okay. So, real, these are the possibilities. If lambda is positive, I can write this as a mu square, okay, where with mu is positive, lambda is this, anyway lambda is 0 is the same, okay. And here also you can make it like lambda equal to minus mu square with mu is positive. So, this is how you make 3 possibilities, and now take the equation. So, that is actually d square y by dx square. So, look at the case 1. So, this is the case 1, this is case 2 and this is case 3. So, we look at the case 1, that is you take the equation d square y by dx square q is 0 plus lambda is now mu square y equal to 0. So, this is a second order equation with constant coefficients. I know its solution by earlier methods. You look for yx as e power kx, okay, y of x you look for e power kx, what you get is you get k square plus mu square equal to 0. So, that gives me k equal to minus mu square. So, that is plus or minus I mu, okay. So, your solution is general solution is y of x equal to some c1 e power I mu x plus c2 into e power minus I mu x, or c1 and c2 are arbitrary constants, or you can also write c1, there is no real part. So, cos mu x plus sin mu x are 2 linearly independent solutions. So, you can write cos mu x plus c2 sin mu x, okay. So, in this case so we have not applied the boundary conditions so far. So, what are the boundary conditions? y0 is 0. So, you apply y0 equal to 0 implies c1 cos mu 0, that is 1 plus c2 0, c2 into 0 into 1, okay, this is 1 plus c2 into sin mu 0 is 0 equal to 0. So, this will give me c1 equal to 0. So, if I apply this boundary condition, now my general solution becomes yx equal to c2 sin mu x, okay. Now, you apply the other boundary condition. So, y at 1 equal to 0. So, if you apply this for this, now you have c2 sin mu equal to 0. Now C2 is, if you take C2 0, then what happens? You get a 0 solution. You are interested to find non-zero solution for a eigenvalue problem. So here also when you write like this, Ly equal to lambda y, okay. So if you want for every lambda, whatever lambda you take, which here in this case I have taken minus mu square, so that is plus mu square. So I am looking for non-zero solution y, okay. So if I want non-zero solution, C2 has to be non-zero, okay. So if I take C2 0, I get only 0 solution. So that means I have only 0 solution. So but I am looking for non-zero solution. So do I have values of mu for which I get C2 non-zero, okay. Still this quantity is 0. So you have, right, sin mu is 0 for certain mu values. If no mu value satisfying sin mu equal to 0, that means C2 is 0 is the only option. That means you do not have any non-zero solution, implies that is that corresponding mu, all those mu values you considered, okay, are not eigenvalues. But here you have C2 is 0 or sin mu equal to 0. But this case we do not take it, because if you take C2 equal to 0, what you get is simply 0 solution, which is not desirable, okay. So this will give me, other option is n pi. Mu is, remember mu is always positive, strictly positive. So n pi, n is from 1, 2, 3 and so on, okay, because mu is always positive. So this implies, what is your solution? Yx equal to C2, you can choose a C2 is sin mu x is the solution of this homogeneous equation. So any constant multiple is also solution, you can take this arbitrary constant as 1. So you have a non-zero solution is, now replace C2, you take it as 1 for each mu, for each n, okay, n is from 1, 2, 3 onwards. What you consider is C2 is 1, so sin n pi x. So these are your solutions, okay. What is your mu? Mu equal to n pi. For each, if when mu is n pi, I have this solution. What is mu? Mu is when mu is n pi, what is actually lambda? Lambda is minus mu square, okay. So that is minus mu square, that is lambda. So that I have minus mu is actually n square pi square, okay. So these are your eigenvalues. Corresponding to this, that is mu equal to n pi, I have corresponding solution yn. You can call this yn because it depends on n, okay. So these are eigen functions, okay. So what you know, so what you have seen is you just found only eigenvalues and eigenfunctions for this regular Sturm-Liouville system, okay. So what else you can do? Now you can also say that these eigenfunctions, no, you have not found so far. So far these are the eigenvalues and eigenfunctions. You still have to see two more possibilities, that is lambda equal to 0 and lambda is less than 0. So you look at the case 2. You found some eigenvalues and eigenfunctions. Now look at the case 2, that is lambda equal to 0. In this case, what happens to your equation y double dash equal to 0? So what is the general solution here? Simply C1x plus C2. So you simply integrate, you will get this arbitrary C1, C2 are arbitrary constants, arbitrary constants. So now you apply y0 equal to 1, y0 is 0, will give me C1 into 0 plus C2 equal to 0, that is nothing but C2 is 0. Now what happens to your general solution? Now simply C1x. Now you apply y at 1 equal to 0, for this you get that is C1 into 1 equal to 0, that is C1 is 0. So this implies, what is your yx now? What you got yx is simply C1 C2 both are 0, so this is the 0, identically 0 for every x in 0 1, Okay. So, that means lambda equal to 0 is not an eigenvalue. Okay. So, you do not have eigenvalues, you do not have eigenfunctions corresponding to lambda equal to 0, because you do not have non-zero solution there. Now, look at the third case, lambda is negative. So, that means lambda is minus mu square, mu is positive. So, in this case y double dash, what is your lambda y? Lambda is minus, right. So, lambda is minus mu square. So, you have a minus mu square y equal to 0. So, what is the general solution here? If you write, again you look for y e power kx kind of solutions, you get k square minus mu square equal to 0. That gives me plus or minus mu. Mu is positive. Okay. So, you have a general solution is yx equal to c1 e power mu x plus c2 e power minus mu x. Now, again you apply these boundary conditions, whatever you have, y0 is 0 will give me c1 plus c2 equal to 0. Okay. So, this will give me c1 equal to minus c2. So, the general solution becomes c1 is minus c2. So, you have c1, c2 I replace with minus or c2, c1, c2 you replace with minus c1. So, what you get is e power mu x minus e power minus mu x. Okay. So, this is equal to c1 by 2, rather 2 times c1 into this is sin hyperbolic mu x. That is your general solution. Now, you apply other boundary condition, y at 1 is 0 will give me now, y at 0 will give me 2 c1 sin hyperbolic 0, that is 0, right. This is 0 into 0 is 0, right. So, c1 is arbitrary constant, y at 1, right, y at 1, sorry. So, this is y at 1. So, it should be sin hyperbolic mu equal to 0. So, again either c1 is 0, if c1 is 0 you do not want, because you want to see whether any, because if c1 is 0 then both c1 and c2 are 0, that implies you have a 0 solution. That means that you do not want, you are just looking for non-zero solution, whether any possible mu you have a non-zero solution. Okay. So, you have to see sin mu hyperbolic mu equal to 0. This will give me what are the values for which mu is, and I know that mu is positive. Okay. So, there is no solution, no mu positive satisfies sin hyperbolic mu equal to 0. That implies what? So, you do not have any mu positive satisfying this one, because lambda equal to minus mu square, mu is strictly positive. So, there is no, so this cannot be 0. So, that implies c1 has to be 0. That implies the general solution becomes completely 0 for every x in 0 1, implies lambda equal to minus mu square for mu positive is not an eigenvalue. So, what you have seen in 3 cases, lambda negative is not an eigenvalue, lambda equal to 0 is not an eigenvalue, only here you get eigenvalues. Okay. Lambda, so case 1, that is for lambda positive you have an eigenvalue, lambda equal to mu square or eigenvalue. So, you found what are the eigenvalues and eigenfunctions, minus n square pi square and sin n pi x are the eigenvalues and eigenvectors, eigenfunctions respectively. So, the answer is solution finally minus n square pi square or eigenvalues, and then sin n pi x or eigenfunctions corresponding to n is from 1, 2, 3 and so on, because n equal to 0 is not an eigenvalue. When n equal to 0, you see that this becomes 0. So, these are your eigenvalues and eigenfunctions. So, you found only first step. What is the second step? So, you can see that these eigenfunctions you can actually verify. Okay. So, you can actually verify these eigenfunctions if you call them as Vn of x, and these are your lambda n's corresponding to n is from 1 to infinity. This Vn and Vm dot product which we defined based on what is your differential operator 0 to 1 sin n pi x sin m pi x dx. Okay. So, actually true, this should be 0 whenever m is not equal to n. So, you can easily verify that this is actually 0 when m is not equal to n. So, but when n equal to m, that is Vn dot Vn, okay, sin square n pi x dx, this is 1 by 2. Okay. So, this is 1 minus cos 2 n pi x divided by 2, this is 0 to 1, right. So, this is what is the integration. So, dx. Okay. So, this is simply because this is sin 2 n pi x, you will get that is between 0 to 1 is 0. So, only this will contribute 1 by 2, that is you get simply 1 by 2 is the answer. So, you see that these functions are eigenfunctions, they are orthogonal, you can easily see, and their dot product when they take the same function. So, this value is half. So, what is the third step which we have seen? We have told, okay, so that any function you take any, let f(x) be any square integrable function, that is integral 0 to 1, that is your domain, modulus of f(x) whole square dx is finite. So, any such function, any f satisfying this, okay, I can write, this is what you have to take, that is the meaning of complete orthogonal eigenfunctions, means any function f, square integrable function f, I can write it as a linear combination of all these eigenfunctions. So, what is a linear combination? You have infinitely many eigenfunctions. So, linear combination is with some arbitrary constants Cn sin n pi x, n is from, you have from 1 to infinity. So, this is what is the meaning. So, f(x) I can write like this. Okay. So, where Cn, how do I find my Cn? If I can write like this, but I still do not know what is my Cn. So, Cn, if you apply the dot product both sides, f(x) with Cn will be dot product with Vn, that is sin n. Okay. So, you can say with some Vm of x equal to, you have Cm, n is only when n equal to m it will contribute, that is actually sin m pi x, and you are multiplying Vm, so this sin m pi x. So, here also you can put it as sin m pi x. Okay. So, this will give me, this is true for every m is from 1 to infinity, this is true. So, this means Cm or Cn, now you can change m as n, both are same. So, Cn, this value we have seen here, so that is a 1 by 2. Okay. So, it means 2 times integral 0 to 1, now this you can write f(x) sin m pi x dx. So, this is exactly your Fourier transform, okay, and this is your Fourier series. Fourier transform of f(x) x is between 0 to 1, any periodic function you can say f(x) is defined between 0 to 1, and let us say you take any function like this, signal is given between time 0 to 1 like this, and 1 to 2 is also it's repeated, same thing, same profile is repeated, like that you can go on. So it's periodically it's there, such a signal you can so you are given this between 0 to 1, you can get this discrete frequencies, these are the frequencies, this is that will give you the Fourier transform, and use once you know all these discrete frequencies, the time signal you break it into discrete frequencies, and finally you can get back your signal itself in terms of these discrete frequencies. These frequencies are Cn's, this number into with these eigenfunctions will give you this is a Fourier series, okay. This actually Fourier series will give you inverse Fourier transform of this, that is a Fourier series here. Inversion of, so you are given a time signal here, you break this signal into discrete frequencies, that is giving Fourier transform is giving that. If you suppose you are given all these Cn's, you want to get back your signal, so that is given by this Fourier series, okay. So that is what is you are seeing here. So as a regular Sturm-Liouville system here, you find the eigenvalues and eigenfunctions, and you see that they are actually they form complete orthogonal functions. Now immediately that means any function I can write as in terms of them, linear combination of these eigenfunctions, that is actually Fourier series. So if I ask you to find here find the Fourier series of given a function, say e power x, you can take e power x, f(x) as e power x, you can write f(x) e power x in terms of all these eigenfunctions sin n pi x. What is actually that? That is actually Fourier series for e power x. E power x is given between 0 to 1 as a signal which is periodically repeated. If you want everywhere, it is not actually e power x everywhere, e power x between 0 to 1 only given. So 1 to 2 is also repeated, same e power x 1 to 2. So whatever profile you have between 0 to 1, e power x, e power 0 is 1, e power 1 is like this, okay. So something like this it will be, right. So same piece it will be repeated at every 1, 2 like that. Such a signal, such a function, if you want such a function you can write so such a function between 0 to 1 which is e power x, you can write in terms of Cn sin n pi x, where Cn's are e power x into sin n pi x dx. So because this is n, so it should be n, okay. This is from n is from 1 to 3 and so on, okay. So this is how you solve, or you see given if you see the differential equation, if you know the differential operator L, okay, if you are given a second order linear differential equation, you can put it in this form, get the L, based on that you define your dot product and then get the eigenvalues and eigenfunctions, you can make a Fourier series, okay. So this Fourier series whatever you have, see the eigenvalues and eigenfunctions, so we will use it to solve partial differential equations, okay, in the future. So let us get back to, so we will do some more examples like regular Sturm-Liouville systems. So now let us go back to the general case, the second case, when what we had is if you are given a differential equation like this, any second order differential equation you are putting it now, px dy by dx into ddx, okay, plus qx into y plus lambda into wx y equal to 0, x belongs to AB, okay. So this is actually your Ly, this is Ly plus lambda y, so Ly equal to minus lambda y. So actually put it in this form where L is minus 1 by omega x, and this one ddx of px ddx plus qx. So this is what you have seen, x is between 0 to 1, x is between a to b. So for this we have shown that if we have shown that any two functions f and g, you have LF g equal to you have that special thing that Px times, okay. So what do you have? That you have seen earlier. I can write without saying. So this Px times Fx let me see, let me take exactly what we got. F into g bar dash, f g bar dash. F g bar dash, that is g dg bar by dx minus g bar df by dx. This one, this whole thing you take, this whole thing you take the limit from a to b plus, and here you get Lg. So this is what you have seen only from this, okay. And the dot product is dot product between f and g. This means here is actually from a to b, wx, that is a weight function. Whenever you have this w, you have to use that is positive, fx gx bar dx. This is what is the dot product which you use here. This is what you have seen. So I want to make this special thing to 0 if I give certain boundary conditions, okay. So let us see in this second case, okay, second test, that is called a periodic system, periodic Sturm-Liouville system. So I define this as Ly equal to lambda y, okay. So x is between a to b. Now I give certain boundary conditions based on if p of a equal to p of b, then what should be the boundary conditions, okay. It is not regular, it is something p of a equal to p of b, but they are not 0 and which are not 0. So that is what is the case. In this case I give the boundary conditions are like this. Boundary conditions are periodic system, you get y at a equal to y at b. You expect the solution is also periodic. So it is like p is periodic, you expect your solutions are also periodic, okay. And then y dash at a is also same as y dash at b. Like this you can give your boundary conditions, okay. These are the boundary conditions. So if you give these boundary conditions, this and this together with this, you can make this term. So now you can see Pb and f g bar dash, okay, g bar dash minus g bar f dash all are at b, okay. So this is one minus, now you apply the limit at x equal to a, so you have a minus p at a, f at a, g bar dash at a minus g bar at a, f dash at a. So this is what you get, that special term becomes this value you can easily see. Now we put Pa equal to Pb, so Pa is common. Now what you have, Fb is also same as Pb, right. Fb equal to Fa, if you apply this boundary condition, let F be the solution of this system, F and G are two solutions of this system, okay. This equation with these boundary conditions, then you have the first boundary condition will give me, now I can replace Fb with Fa. Similarly G bar is also another solution. So this G bar is another solution, G bar at A, G bar dash at A is same as G bar dash at B. So you apply the second here, so you get G bar dash at A. Similarly here, so because G, now for G bar is a solution and you apply the first condition, you get G bar at A. And similarly for F dash, for F is a solution of the system, you apply the second condition for F dash at A. and this is same as a second one. So, this is repeated P of A, this you write as it is. So, both are same. So, this is actually equal to 0. Okay. So, that means you made this this term 0 again if I provide these boundary conditions. So, this is periodic Sturm-Liouville system. So, if you can give to your differential equation this eigenvalue problem with these boundary conditions, that also make this operator L Hermitian or self-adjoint or skew symmetric. Okay. So, this is another case, this is case 2. So, this is a periodic system. So, what else what are the other forms you can. So, what is left is, now if P of A is 0 or P of B is 0 or both are 0, in that case what boundary conditions you have to give to make this special terms, this boundary term 0. Okay. We will see that is called a singular Sturm-Liouville system. So, what is actually P? P is actually here. So, P, if P is 0, that is the coefficient of second order derivative, highest derivative. If P is 0, P at A is 0, that means A is a singular point, right. If A is singular point. So, B is also singular point if P of B is 0. Both are 0, A, B are singular point, like you have seen for Legendre equation. Okay. Legendre equation is defined 1 minus x square y dash y, right, y double dash. So, you can see that P of x is 1 minus x square there. You see that 0, minus 1 and plus 1 both are 0, they are is like that. So, that is an example. You can see that there is a possibility for certain equations for both P of A, P of B, both are 0. So, in such a case, so you see that P of A is 0, P of B is 0 or one of them is 0, and this quantity, when can you say that 0 into something you want to 0? Is it 0? 0 into something is 0, this something, if you want this to be 0, this something has to be finite. Okay. Because 0 into infinity you cannot say, it is indefinite. Okay. Indefinite, this can be anything. Okay. This can be even some non-zero quantity. So, you have to make sure that this quantity is finite. Okay. So, how can you make sure? So, that is that you are giving through your boundary conditions. If P of A is 0, okay, then you make sure that this quantity at A is also 0. That means f or any solution f and its derivative, this one, or g its derivative has to be bounded at A, that is the condition, right. F and g bar are solutions, f and f dash or g and g bar and its g bar dash, they are the solutions, right. G and g bar, if they are bounded, if you say that a solution and its derivative is bounded at x equal to A, that makes sure that this quantity is finite. Okay. This quantity is finite. So, the finite into P at A is 0, that is known. So, 0 into finite quantity is 0, that makes this term is 0 at x equal to A. If P at B is also 0, okay, then you have 0 here and you can make this 0. Okay. So, this you have to make sure that f and its derivative, a solution and its derivatives are also bounded at B, then together it will become 0. Okay. Normally you see either both of them are 0. So, that is rare that one side it is 0 and the other side is non-zero. Okay. What happens if PB is non-zero? PA is 0, PB is non-zero. Let us say PB is non-zero, you have to make sure that this quantity is 0. Okay. If you want this quantity is 0, either you have to give the second boundary condition, like because PB is non-zero, okay, then either f is at B is 0 or its derivative at B is 0. One of these you can give, you can fix your boundary conditions. Okay. So, we will see this as a singular Sturm-Liouville system. Okay. Singular Sturm-Liouville system. Again you have Ly equal to lambda y, x is between A to B, and what you will see the three different cases here. P of A equal to P of B, sorry, P of A is 0 and P of B is 0. So, you have three cases, this or P of B is 0 or both P of A equal to 0 and P of B equal to 0. So, this is case 1, this is case 2, this is case 3. Okay. So, in this case, first case, okay, let us look at the case 3 as first one. Okay. So, if you want this, you write it as this and this both are 0, this you put it as R. So, that this is your case 1 and this is your case 2 and this is your case 3. So, let us look at the case 1 where both PA and PB are 0. Okay. Case 1. So, case 1, so you want that special term, that is, if you look at this, so that is this one P of B. So, what are the boundary conditions you give? So, boundary conditions for case 1 when P of A, P of B is 0 are y and y at A and y at B or y dash at A are finite. Okay. If y is finite and y is defined between A to B and at the boundary it is finite, its derivative when it exists it is also finite. Okay. So, that is how you can say that both will be together will be true if y a is finite. Okay. And other boundary condition is y b and y dash b are finite. So, these are your boundary conditions. If with these boundary conditions, this equation you can make this quantity, because now this PA PB both are 0 into your make, because of these boundary conditions y and b, f and g bar are satisfying these two boundary conditions, that make this quantity and this quantity is finite. So, 0 into finite 0 minus 0 into finite finally 0. So, you see that again that special term here is a boundary term is 0. So, what you have seen is LFG equal to FLG dot product. So, again you see that this is Hermitian. So, you can see that now once you get here immediately say that L is Hermitian. Okay. L is Hermitian in the earlier case. Now, in the singular Sturm-Liouville system case also L is Hermitian. Now, what is the case 2? Case 2 or case 3, we will see boundary conditions will be, because P of A is 0, I want to make sure that this quantity is 0. So, you have to give the same boundary conditions, this y at A, y at B and y dash at A are finite, that is first boundary condition 1. Okay. The second boundary conditions, because P of A is only known, okay, P of B may be non-zero, that means P of B is non-zero. If P of B is non-zero, I have a non-zero, so P of B is non-zero, this quantity. So, when this will become 0 together, so this becomes 0, this is non-zero into, if you want to make this 0, f at B, f g bar at B, either this or a derivative value at B has to be 0. So, your solution, you can give two boundary conditions y at B equal to 0, okay, or same boundary condition for the first one, y of A and y dash at A are finite, or y dash at B is 0. So, either of these boundary conditions will work, make this special term 0, okay. So, that you have LFG, that is L will be self adjoint. So, this again implies make it L as Hermitian. Case 3 is simply repetition of case 2. Case 3 is simply replace boundary conditions, simply instead of A you interchange A and B, okay, simply write for the sake of completeness. So, you can give these boundary conditions for Ly equal to lambda y at A equal to 0, okay, and y at B, y dash at B are finite, okay, or these boundary conditions y dash at A equal to 0 and y at B and y dash at B are finite. With these boundary conditions you make this boundary terms will be 0. So, that makes the differential operator as self-adjoint or Hermitian or skew symmetry. Okay. So, once it is Hermitian, so you can just find the eigenvalues and eigenfunctions. Okay. So, the inner product is same, the dot product is here, the dot product is a periodic system. What is the dot product here? So, whatever once you have the Hermitian, and you can you have seen the dot product is same. So, that is A to B, we have written already. So, the dot product is same. So, this is what you always, okay, it does not change here. So, we will see the examples in each of these cases for the periodic Sturm-Liouville system and singular Sturm-Liouville system in the next video. We will see these two special Sturm-Liouville systems, periodic Sturm-Liouville system and singular Sturm-Liouville system. So, when you are given a differential equation as an eigenvalue problem with this one of these boundary conditions, so you can see that it will be either regular or periodic or singular Sturm-Liouville systems. So, I have given an example for the regular Sturm-Liouville system, and the next video we will have examples for periodic and singular Sturm-Liouville systems. Okay.